This commercial aircraft is in stable flight, right up until the moment it experiences a sudden, uncommanded pitch shift. This CAD animation shows the flight control actuator responsible for that exact movement. Prior to flight, this component passed every isolated unit test and met all baseline engineering requirements. But the catastrophic failure originated outside the actuator. It was caused by a ruptured shared hydraulic return line. This shared dependency went entirely unnoticed because the engineering teams analyzed the components in isolation rather than evaluating the system as a whole. Testing individual components from the bottom up is insufficient to prevent catastrophic system-level disasters in integrated aerospace architectures. Title 14, Section 25.1309 of the Code of Federal Regulations mandates that no catastrophic failure condition can result from any single failure. Modern aircraft architectures are too densely integrated for human intuition to reliably catalog every possible failure state. Aviation authorities demand concrete mathematical proof that all credible failures have been identified, understood, and mitigated. Generating this proof requires two orthogonal lenses: failure mode and effects analysis, which is inductive, and fault tree analysis, which is deductive. These two methodologies serve as the dual cornerstones of the ARP 4761A safety assessment. Neither can guarantee safety without the other. Failure mode and effects analysis, or FMEA, is an inductive bottom-up framework that asks one core question: how can this specific part fail? Consider an electric propulsion inverter used in modern flight architectures. This electrical schematic shows how the analysis begins at the lowest component level. Here, we isolate a single MOSFET. We then determine what happens when this specific MOSFET suffers a short circuit. Engineers document this using a tabular FMEA grid. The failure mode column logs the MOSFET short. Tracing the ripple effect, the local failure causes a subsystem phase imbalance, which is logged into the next column. The induction completes when we map that subsystem error to the ultimate system effect, a total loss of thrust. FMEA assigns severity and occurrence ratings to drive physical design changes. Its flaw is that it analyzes only one component at a time. Fault tree analysis, or FTA, is the deductive top-down counterpart to FMEA. FTA asks the opposite question: what exact combinations of faults must occur to cause a specific disaster? This diagram establishes the top event. Here it is the catastrophic loss of flight control power. From there, the downward cascade initiates. Engineers logically deduce what immediate failures trigger the top event. The first requirement is a total failure of the primary hydraulic pump. The second requirement is a concurrent failure of the backup electric pump. Boolean logic acts as the glue holding this model together. An AND gate mandates that both the primary and backup systems must fail simultaneously for the disaster to occur. OR gates represent single points of failure where the system lacks required redundancy, continuing the branch downward into lower-level component faults. FTA models shared dependencies, capturing the complex, multi-point failures that FMEA inherently ignores. The primary output of a qualitative FTA is the identification of minimal cut sets. In this diagram, a minimal cut set is the absolute smallest combination of independent events that will trigger the top event. To satisfy certification authorities, these cut sets must be mathematically quantified. The failure rate probabilities derived from the A are inserted into the base nodes of the fault tree. The probability of component A multiplying against component B calculates the overall risk of the top event. Calculating minimal cut sets allows organizations to pinpoint the exact failure paths that contribute most heavily to catastrophic risk, directing engineering resources exactly where they are needed most. Aerospace standards mandate both methodologies because relying on just one leaves dangerous blind spots. Recall the shared hydraulic return line failure from the opening of this video. This diagram shows how physical layout and spatial proximity can create common cause failures across entirely different subsystems. A component-level FMEA is blind to spatial vulnerabilities because it assumes all external conditions remain perfect. FTA mitigates this by allowing engineers to explicitly map those spatial overlaps as shared logic gates. FMEA provides the critical component vocabulary, while FTA provides the systemic grammar. Without those, the safety assessment lacks the logical structure required to account for complex cross-system failures. In aerospace engineering, all of this data is organized into a strict ARP 4761A compliance package. This flowchart shows bottom-up FMEA data synthesizing into the failure modes and effects summary, forming the qualitative bedrock for the system safety assessment. Simultaneously, top-down FTA data must prove the system meets strict quantitative targets, like 1 failure per billion flight hours, satisfying development assurance level compliance. This interconnected data pipeline is the only accepted method to prove to regulatory bodies that a highly integrated architecture is safe to build. Discovering an architectural flaw late in the development cycle due to poor initial safety analysis has severe real-world consequences. Failing to identify a single minimal cut set can invalidate months of expensive hardware testing and ground a multi-billion-dollar program indefinitely. These logical proofs must be finalized and verified before manufacturing is ever authorized to begin. Combined, FMEA and FTA serve as a mathematical verification layer, ensuring safety requirements are physically rooted in the architecture before a single part is manufactured. The ultimate success of this rigor is an aircraft executing its mission with a stability verified by every logic gate mapped during the design phase. FMEA and FTA translate abstract safety goals into a flight-ready reality, setting the stage for the next phase, integrating these models into the preliminary system safety assessment.